Every architecture diagram has a database, usually one. Clients, load balancers, API servers, these are all redundant. If one API server goes down, the others handle the traffic. But the database? There's one. If it goes down, everything goes down with it. It doesn't matter how many redundant servers you have upstream. If they all depend on one database that's offline, your system is offline. Beyond availability, every read and every write competes for the same CPU, memory, and disk (IO) on that single instance. As traffic grows, that one database becomes the ceiling for your entire system's throughput. The obvious answer? Don't have just one. Replicate. But the moment you replicate, you step into a trade-off that will define every database architecture decision from here on. We'll emphasize AWS throughout, but the theory applies everywhere. Later, we'll reference Google Cloud Spanner and Azure for comparison. Quick vocabulary first, because these terms will come back throughout. The compute layer is the brain. It parses queries, manages transactions, maintains buffer cache. The storage layer is the disk. It persists data pages and the write-ahead log. The replication layer keeps copies aligned across instances. When we say replicate, we mean running multiple copies of the database. The primary, also called the master or writer, is the one instance that accepts all write operations, inserts, updates, deletes. It's the source of truth. Read replicas are copies that only serve read queries. Select statements. They receive changes from the primary and apply them to stay in sync, but they never accept writes directly. Clients that need to read data can go to any replica, spreading the load across multiple machines. Clients that need to write still go to the primary. Since reads are typically 80 to 90% of database traffic, offloading them to replicas massively reduces the load on the primary. The primary streams changes to replicas using write-ahead log, or WAL, replication. The order matters. Step 1. The primary writes a WAL record to its own disk first, byte-level changes. Like at page 4782, offset 96, change these bytes. The log hits disk before the actual data page is updated. That's the write-ahead part. Step 2. It applies the change and commits the transaction. Step 3. Only after successful commit does it ship the WAL to replicas. If the transaction failed, say a foreign key violation, it rolls back. No WAL shipped. Replicas never see failed transactions. Step 4. Each replica replays the WAL by applying byte-level changes to its own storage. It does not re-execute the SQL. This replay can fall behind under heavy writes. That's replication lag. For availability, you configure a standby replica that auto-promotes if the primary dies. On AWS, multi-AZ deployment gives you a synchronous standby in a different availability zone. If the primary fails, failover happens in 60 to 120 seconds. Good. We're no longer a single point of failure, but something important just happened that we need to talk about. A user writes data to the primary. Milliseconds later, they read from a replica. The replica hasn't caught up. They get stale data. You traded consistency for availability. You now have a system that's always available for reads, but not always returning the latest data. You may not have thought of it this way, but you just made a CAP decision. The CAP theorem says a distributed system can guarantee at most 2 of 3 properties. Consistency, every read returns the most recent write, all nodes see the same data at the same time. Availability, every request gets a response. Partition tolerance, the system keeps working when network communication between nodes fails. Let's be precise about partition. In CAP, a partition is a network split. Two database nodes are both alive and running, but they can't communicate with each other. A router failed, a cable was cut, a firewall misconfigured. Both databases are up, but they've lost contact. Partitions are inevitable means. No matter how good your network is, at some point, your database nodes will lose the ability to talk to each other. When that happens, the system must choose. Does it refuse to serve requests until communication is restored, sacrificing availability to preserve consistency? Or does it keep serving from both nodes, knowing they might diverge, sacrificing consistency to preserve availability? That's the real choice. You don't pick two. Partitions will happen. You pick whether to sacrifice C or A when they do. SQL databases make 4 guarantees known as ACED: atomicity, all or nothing. If any part of a transaction fails, the entire thing is undone. Transfer $100 from account A to account B. If the debit succeeds but the credit fails, the debit is reversed. Consistency. Every transaction moves the database from one valid state to another. Constraints, foreign keys, and rules are always enforced. Isolation. Concurrent transactions don't interfere. Each behaves as if it's running alone. Durability. Once committed, it stays committed, even if the server crashes 1 millisecond later. Every one of these guarantees requires coordination between nodes in a distributed system. That coordination is where the problems start, and it's why NoSQL was created. Eventually consistent means, after a write to the primary, all replicas will converge to the same state, but not immediately. There's a lag window. How big that window is determines where you sit on the CAP spectrum. With Aurora, it's about 20 milliseconds. Cross-region, it can be a second. At the edge with disconnected devices, it can be hours or days. An important clarification: eventual consistency is not a NoSQL concept. It's a CAP concept that applies to any distributed system with replicas. Aurora's red replicas are eventually consistent right now, and Aurora is a SQL database. The difference is in attitude. SQL databases treat eventual consistency as an unfortunate side effect of replication that they try to minimize. NoSQL databases treat it as a deliberate design choice they embrace. Both use it. They just have different attitudes toward it. Before we continue along the CAP spectrum, we need a brief detour. Understanding why NoSQL exists will make everything that follows click. And it comes from a different problem than the one we've been discussing. Not replication, but sharding. We've been talking about replication, making copies of the same data on multiple servers. ACID actually works fine here. The primary handles all writes normally, and replicas are just trailing copies. The only issue is how fast replicas catch up. That's the CAP consistency question. Sharding is different. It means splitting different data across different servers. Users A through M on server 1, users N through Z on server 2. No single server has the complete data set, and this is where ACID gets truly hard. In the late 2000s, Google, Amazon, and Facebook hit the limits of vertical scaling. They needed horizontal scaling, adding more commodity servers. That meant sharding. Imagine a SQL database sharded across 5 servers. A user transfers $100 from account A on server 1 to account B on server 3. ACID says this must be atomic. To guarantee this across 2 servers, you need a 2-phase commit. Phase 1, prepare. A coordinator asks server 1, can you debit $100? And server 3, can you credit $100? Both must respond yes before anything happens. That's 2 network round trips. If either server is slow, both wait. Phase 2, commit. The coordinator tells both servers, go ahead. 2 more round trips. If the coordinator crashes between phases, both servers are stuck holding locks. waiting for an instruction that may never come. Now, multiply this by thousands of transactions per second across 5 servers, each potentially touching data on multiple other servers. Every transaction waits for round trips. Every server holds locks while waiting. Those held locks block other transactions, which are also waiting, which are also holding locks. The contention compounds. Adding more servers makes things slower because the coordination overhead grows faster than the throughput gains. That's the coordination tax. It's not that it's impossible. DSQL and Spanner prove it's possible with enough engineering. But at the scale Google and Amazon were operating, it was cheaper to redesign the data model. So they dropped ACID's guarantees. No foreign keys, no multi-record transactions, no schema enforcement across nodes. Google published Bigtable in 2006. Amazon published the Dynamo paper in 2007. Facebook released Cassandra in 2008. These weren't anti-SQL. They were pro-horizontal scaling. So NoSQL dropped ACID for sharding reasons. But here's why this detour matters for our CAP story. The same guarantees NoSQL dropped: foreign keys, multi-record transactions, schema enforcement, are exactly the ones that determine how far right you can go on the CAP spectrum. By dropping them, NoSQL didn't just solve the sharding problem, it freed itself to handle eventual consistency and disconnected operation on the replication side too. That's why NoSQL can reach position 5 on the spectrum, and SQL can't. NoSQL isn't one position on the spectrum, it's a data model that can live anywhere. DynamoDB with strong consistency reads is near position 1. DynamoDB Global Tables with multi-region writes is position 3 to 4. A database running locally on a phone, syncing when reconnected, is position 5. SQL can operate at positions 1 through 4, but hits a wall. NoSQL can go all the way to 5. Now, let's walk through each position on the spectrum. Standard RDS, where each instance has its own Amazon EBS, Elastic Block Store, essentially a virtual hard drive attached to the instance, and WAL is shipped between replicas, gives you position 2 with seconds of lag. Aurora does something architecturally radical to make position 2 much better. Aurora separates compute from storage. All instances read from a shared storage layer, replicated 6 ways across 3 availability zones. The storage nodes are not dumb disks. They're programs with CPUs that understand database pages. In standard RDS, the compute layer does replay work. In Aurora, the storage layer does it. Replicas just read from shared storage. The primary sends only tiny cache invalidation hints. Lag drops from seconds to under 20 milliseconds. The storage quorum: writes need 4 out of 6 nodes, reads need 3 out of 6, keeps availability high without giving up consistency on the primary. Aurora gives you 2 endpoints: a cluster endpoint pointing to the primary for strong consistency, and a reader endpoint for replicas with eventual consistency, about 20 milliseconds of lag. Your application chooses per query. Financial balance checks go to the primary. Product browsing goes to replicas. You're choosing your CAP position per query. Now you want to survive an entire regional outage. It's important to distinguish 3 different things on AWS. Aurora Standard runs in a single region, primary, and up to 15 read replicas, all within one AWS region. It cannot write in multiple regions. Aurora Global Database is an add-on that replicates an Aurora cluster to other regions. But it's not multi-region writes. You still have one primary in one region, handling all writes. Other regions get read-only replicas with under 1 second of async lag. If the primary region goes down, you promote a secondary. But only one region writes at a time. It's for disaster recovery and low-latency global reads, not distributed writes. Aurora DSQL is a completely different product, which we'll cover next. Active-active writes across regions with strong consistency. Different architecture entirely. With Aurora Global Database, you've moved to position 3 on the spectrum. More availability, more eventual consistency. The acceptable data loss during failover is your RPO, recovery point objective. How much recent data you're willing to lose. If your write throughput exceeds what one primary can handle, sharding, splitting data across independent databases, is the traditional answer. But cross-shard joins are impossible. Cross-shard transactions need the saga pattern, and resharding live data is painful. Sharding is a last resort. DSQL was designed to eliminate it. Everything so far has been a progression rightward, trading consistency for availability. DSQL and Spanner attempt something different, moving right on availability without moving left on consistency. Engineering around CAP? Aurora DSQL is a serverless, distributed SQL database with multi-region active-active writes and strong consistency. Generally available since May 2025, every region can write. Reads from any region return the latest data. No sharding required. This is fundamentally different from Aurora Global Database, which only allows writes in one region. 2 innovations make this possible. Amazon Time Sync Service uses hardware atomic clocks on every EC2 instance for microsecond accurate global time. And DSQL uses optimistic concurrency control. Transactions run freely, conflicts checked only at commit time, then writes parallelized across all regions simultaneously. The architecture is disaggregated into independent components: query processor, adjudicator, journal, crossbar, each scaling independently. Robinhood is exploring replacing hundreds of database shards with a single DSQL endpoint. Google Cloud Spanner has done this since 2017, 8 years before DSQL. Google's TrueTime API uses atomic clocks and GPS receivers. Battle-tested at Google scale. AdWords, YouTube. Spanner works truly globally, not continent-limited like DSQL. Azure has no equivalent in this category yet. DSQL and Spanner don't break the CAP theorem. They engineer around it within controlled environments, data centers connected by high-bandwidth fiber. DSQL's optimistic concurrency means high-contention workloads see transaction aborts. It doesn't support full PostgreSQL. No foreign keys, no triggers. And DSQL is continent-only for now. The KP position: strong consistency with high availability between data centers, but not at the true edge. That's next. DSQL and Spanner solved server-to-server distribution. True edge computing is different. Your nodes are phones in subways, IoT sensors in fields, laptops on airplanes. The network is slow, unreliable, and frequently absent. The distinction: ACID can't do disconnected. Even before conflicts, atomicity across disconnected nodes means two-phase commit. Nodes in Tokyo and London means about 250 milliseconds per round trip per phase. A 5 millisecond local write becomes 500 milliseconds or more. Isolation needs distributed locks, another ocean crossing per write. Under load, the same compounding contention we discussed, but across continents. Remember the 4 ACID guarantees? At the edge, each one creates a specific problem with no resolution. Atomicity. 2 nodes commit conflicting transactions independently. Both durably committed. You can't roll back either. 2 contradictory all results with no undo mechanism across independent nodes. Consistency. Node A inserts an order referencing user 123. Node B deletes user 123, both locally valid. On sync, an order pointing to a deleted user. Foreign keys can't span disconnected nodes. Isolation: 2 disconnected nodes are, by definition, not isolated from each other. No way to detect conflicts until they sync. Durability. Both conflicting writes are durable. The guarantee that's meant to protect data now prevents resolving the conflict. This is the payoff of everything we've discussed. NoSQL doesn't solve these edge problems. It sidesteps them entirely by not making the promises that create them in the first place. No multi-record atomicity means no multi-record conflicts. No foreign keys means no constraint violations on sync. No isolation expectations means concurrent writes on different nodes are expected, not an error. Durability of both conflicting writes is a feature. The merge strategy is designed to converge two states into one. Eventual consistency isn't a weakness of NoSQL. It's the deliberate design choice that makes everything else possible. Local writes in milliseconds, async sync, edge-native operation. But not all NoSQL is built for the edge. DynamoDB and MongoDB are the most popular NoSQL databases, but they're cloud-hosted services. Your application still needs a network connection to reach them. Phone in a subway? IoT sensor with no signal? The database is in the cloud, and the cloud is unreachable. They're excellent for distributing data across data centers, but neither runs on the device itself. TruePosition 5 requires a database that runs locally on the device. MongoDB Atlas Device Sync, formerly Realm, is designed exactly for this. A lightweight MongoDB instance runs directly on the device. Users read and write locally with zero latency, even with no network. When the device reconnects, Device Sync handles replication automatically. Conflict resolution rules are configurable per collection. The default is last write wins at the field level. The sync protocol is built into the database. Your app just reads and writes normally. Conflict-free replicated data types, or CRDTs, are data structures designed so concurrent modifications on different nodes always converge without coordination. A CRDT counter incremented by 3 on one node and 5 on another gives 8 on sync. Both writes preserved. Redis Enterprise uses CRDTs for its active-active geodistribution. The conflict resolution spectrum ranges from fully automatic to configurable. Last write wins, zero code, may silently lose data, DynamoDB global tables. CRDTs, zero code, no data loss, limited types, Redis active-active. Field level merge, automatic for different fields, MongoDB. Custom rules. You define resolution rules per collection. MongoDB Device Sync. Most production systems use a hybrid, automatic for common cases, custom rules where business logic demands it. OpenAI serves 800 million ChatGPT users on Azure Database for PostgreSQL. 1 uncharted primary, nearly 50 read replicas, 10-fold load growth in a year. 5 nines availability, where are they on the spectrum? Position 2, single primary for strong consistency on writes. Read replicas for availability on reads. They didn't reach for DSQL or Spanner, or NoSQL. They chose a position and optimized ruthlessly. Connection pooling, strict schema discipline, rate-limited backfills. Write-heavy workloads that outgrew position 2 got migrated to a NoSQL database, moving those specific workloads rightward on the spectrum. The lesson? The CAP spectrum isn't a ladder to climb. It's a set of positions to choose from. Picking the right one matters more than picking the most advanced technology. Every database architecture decision is a position on the CAP spectrum. A single primary gives you strong consistency and a single point of failure. Add replicas, and you trade consistency for availability. Push to multi-region with Aurora Global Database, and the lag grows. DSQL and Spanner try to recover strong consistency at global scale using atomic clocks, engineering around CAP within controlled networks. And at the true edge, disconnected devices, unreliable networks, ACID coordination becomes structurally impossible. And NoSQL with CRDTs is the only answer. NoSQL wasn't created because SQL was bad. It was created because companies needed horizontal scaling, and ACID's coordination overhead was the obstacle. Dropping those guarantees was the price of admission to the right side of the spectrum. There is no correct position. There is only the position that matches your workload. OpenAI proved you can serve 800 million users from position 2. DSQL proved you can recover consistency at continental scale. MongoDB Device Sync proved you can build applications that work with no network at all. They're all valid. The art is knowing which one is yours. Thanks for watching. Subscribe for more system design deep dives. Next video: Event-Driven Architecture from the Ground Up. See you there.